Alright, welcome everyone to the final stream for discrete math, at least in terms of the sequence of topics that we want to cover in discrete math. We have started from logic, we worked our way to sets, relations, functions. Last round we looked at graphs, and now we're going to look at a special kind of graphs called a tree. And we're actually going to use ideas that we developed the last time in graphs to talk about trees. So today we are gonna let's just warm up first before we dive into trees. Let's first draw the graph given by these pieces of information. We have the vertices 1 to 9, and we have these edges 1, 2, 2, 3, 4, 5, 6, 7, 6, 8, 7, 8, 8, 9. And just a recap that this idea is that, okay, we have vertices 1 and 2, and since 1 and 2 are connected in the edge set, they'll be connected in the graph like this. And likewise, 2 and 3 are connected, so we can put 2 and 3 together like this. And we can repeat for each of the vertices. 4 and 5 go together. 6 and 7 go together. 6 and 8 go together, so we can connect the 8 over here. 7 connects to 8, so we can draw a connection there. And 8 connects to 9, so 8 will connect to 9 like this. So that's just a quick recap on how to use the data to draw the graphs. And we're going to need this because we're going to ask a few questions about this graph. So for example, find the number of graphs that have the same vertices as G, and yet they're isomorphic to G. So what do we mean by that? We mean, for example, if you consider this graph like this, instead of 1, 2, 3, you have 3, 1, 2, and then you have 6, 7, 9, 8. These two graphs are not the same. Nevertheless, they are isomorphic. They do have the same shape. So we want to ask how many possible different graphs can we obtain? Well, it might be instructive to first identify the shape of the graph, which looks a bit like this. And perhaps we could use some counting arguments in order to count the number of possible isomorphic graphs, meaning different labelings, same shape. Right? We want isomorphic graphs, different labels, same shape. So what can we do? Perhaps we could first choose the numbers to go inside the line, this line, and then the cycle, and we'll explain that in just a little bit of detail. So let's first count the number of different combinations of numbers. That gives us, well, for the first one, we have 3 spots, so we need 3 different numbers. So that is 9 out of the 9 different numbers, out of the 9 different vertices, we need to choose 3 of them. Right? And then we'll need to multiply by some number that helps us determine the arrangements. And how about for this part? Well, once we have 3 numbers, we are left with 6 digits and 6 vertices, and we need 2 of them, so we'll choose 2 from the 6 vertices. Now, for reasons which I'm going to explain later, let's choose 3 numbers or 3 vertices to form the cycle, and I'm going to explain why that's useful in just a moment. So we have a total of 4 after we have gotten rid of 5 different numbers. We are left with 4 numbers. We're left with 4 different vertices. So 4 vertices, we need to choose 3 of them to go into the cycle. Now I'll explain why this is going to be important. So let's come back to this particular collection of this part of the graph, and we see that once we have 3 numbers, we can arrange them in many different ways. In fact, we can arrange them in any of these forms: 1, 2, 3, for example, or 1, 3, 2, or 2, 3, 1, or 2, 1, 3, or 3, 1, 2, or 3, 2, 1. We could arrange them in all of these ways. But do we get 6 different graphs? The answer is no, we don't get 6 different graphs. The reason being that 1, 2, 3, if you label 1, 2, 3 this way, is the exact same graph as the 1, 2, 3 if you label it this way. You just need to swap everything and you get the same graph, which tells us that actually we have a bunch of duplicates that we can get rid of. So for example, 3, 2, 1 is repeated by 1, 2, 3. 3, 1, 2 is repeated by 2, 1, 3. And 2, 3, 1 is repeated by 1, 3, 2. So we're actually only left with these different arrangements. But how many did we get rid of? We got rid of exactly half of the number of possible permutations. Because for every permutation this way, you get the exact same tree for the permutation in this way. And what that tells us is that we can write this as 3 factorial over 2. In fact, this kind of works in general, right? If you have a total of n vertices, then the total number of arrangements here is going to be number of arrangements is going to be n factorial over 2, because if you go in this direction and this direction, you're going to get the same graph. So what about this one? Now, if you were to write 4, 5 here and 5, 4 here, they're obviously the same. But let's just put 2 factorial over 2, just to emphasize that we can apply the same process whenever we have at least 2 vertices. And finally, we only chose 3 numbers. So for example, 6, 7, 8, just for instance. How many arrangements can we form using this setup? Well, how many can we form is, if you think about it, you could arrange them in many different ways. 6, 7, 8, 6, 8, 7, 7, 6, 8, and so on and so forth. But you'll notice really, really quickly that they all actually give you the exact same graph. It's the same cycle, in fact. So there's only one permutation of these guys. But what about this last guy? Could I put a 9, could I put a 9, attach it to a 6? Well, I could. And could I put a 9 and attach it to a 7? Well, I could too, and I can actually get different graphs. So this extra little bit over here can attach to any of these guys. We have a total of 3 choices there, and so the number is 3. So we have 3 choices, and doing a quick calculation is going to give us the final answer. And I'm going to let you check that this gives you the final answer. Okay, so let you check that we do get the number of interest here. But on the other hand, now let's go to the real meat of the question, which is the idea of a tree, right? So here is the question again. We're going to still need the same graph, but now we're asked to find the subgraphs of G that 1 is a tree, and secondly, it contains the vertex 7. Now, what is a tree? Informally, a tree looks a bit like this. Right? There we go. That's a tree. But we're looking at this from a technical math class. So what do we mean by a tree? If a graph is a tree, if it satisfies 2 conditions, it's connected and it's not cyclic. In other words, can you connect them like this? There we go. That's connected and not cyclic. Here's one which is connected and yet cyclic, right? And here's one which is not cyclic but not connected, right? So a tree requires both not being cyclic and being connected. Both are really, really important conditions for our definition of a tree. Now, we want to find the subgraphs of G that is a tree, and it contains the vertex 7. And what that tells us is that, well, here's the vertex 7. If we were to contain any other vertex, there's no way we can connect it to 7. Any one of these guys, there's no way we can connect it to 7 at all. Which tells us that any subgraph of 7 is going to have to, well, any subgraph of G that contains 7 can only stay on this island. That's the only island we can afford. Now, this island can have a bunch of different people, right? It could have one person, two persons, or three persons. So let's see. If the island's only one person, then that's just 7. If it's two persons, it could be 7, 6, or 7, 8. Now, we can't have 7 and 9 because these two things are not connected by an edge, so that doesn't work. But what about 3 people? Now, 3 people gets interesting because you could have 7, 6, 7, 8, right? You could have 6, 7, 8. Okay, it might be a bit tricky to deal with the 3 people case because there's so many ways to do it. But here's how we might go about it. From the 7, 6 graph, we could attach an 8 to the 6. Or we could attach it to the 7. So what I mean we could either attach the 8 here, or we could attach the 8 here. We can attach the 8 either to the 6 or the 7. Now you could do the same thing with the 7, 8 bit. If you attached 6 to 8, then you're actually, I think we're getting a new graph. Yeah, we're getting a new graph, right? So repeat the same game with 7 and 8. If we attach the 6 to 8, we actually get a completely different subgraph. But if we attach the 6 to a 7, this is basically the same graph as this one. Because this is 6, 7, 8, this is just 6, 7, 8. And here's a very interesting big picture idea. When you're building up larger graphs, you can use smaller graphs to build up larger graphs, right? How do we build these up? We just slowly added one node to each of the different existing subgraphs. And finally, we can go one step further, right? We can actually go one step further right here. Each of the 8s, you could tag on the 9. You can tag on the 9, you can not tag on the 9, either option, you will be able to get another tree, right? So here's one. This itself is one tree, but if you include the 9, you get a second tree. And you can do the same thing with all of the other instances of the 8s. Right? So how many graphs do we have in total? 1, 2, 3, 4, 5, 6, 7, 8, 9, and finally 10. You have a total of 10 different graphs. Total number of trees is 10. Right? Total number of trees that contain the vertex 7, to be more precise. If you contain a different vertex, you're going to draw different subgraphs. I think that makes intuitive sense. But that's the definition. A graph is a tree if it's connected and not cyclic. So we can try to explore this idea a bit more. So for example, we'll let n be 1, 2, 3, and 4. We want to find the number of trees whose vertices are 1 to n. And how are we going to do that? Ironically, we might want to first obtain all the different possible shapes and then fill in all the different possible vertices. So let's check them one at a time. In the n equals to 1 situation, we are left with, we want to find the number of trees with one vertex. So here's one vertex. It's connected, it's acyclic, and you can't really create anything else because that's the only vertex. If you do create anything else, you're going to get a loop. And that is cyclic, and we do not want cyclic. Cyclic is not good for our purposes. So that's n equals 1. But this is actually really interesting. For n equals to 2, you could just bash out the definition, or you could build it up from the n equals to 1 situation. And this idea of building bigger things from smaller things is going to be really useful for us, because that's essentially what we mean by the method of math induction. Now, you've probably memorized it as a proof technique, but you can refer to it as a solving technique as well. How do you build bigger objects? We use smaller objects. And so, to build up the n equals to 2 case, you can start with the n equals to 1 case, and ask yourself, where can we connect an edge and a vertex? There's only one, right? This is the edge, and this is the vertex. That's that. Now for n equals to 3, we could ask the same approach. Start with the n equals to 2 situation, and now ask where can we tag on a third edge, a second edge and a third vertex. And you can either tag it on here or here, right? If you tag it on here, this gets you a tree. If you tag it on here, this gets you another tree. But you realize really quickly that they actually have the same shape. And so, for the n equals to 3 situation, you can just tag it on right there. You might be thinking, would the pattern continue for n equals to 4? Right? It's all straight lines. Next one should be a straight line. Let's find out. Start with the n equals to 3 case and ask ourselves, can we tag on an extra edge and an extra vertex? We can tag it on here. We can tag it on here. And we could tag it on here. But this time around, something fishy happens. These two graphs are the same in terms of the shape. But this one is totally different because this guy has 3 intersections. It's connected to 3 other points. And so now, for the n equals to 4 case, we actually get an extra pattern. We actually get this pattern here. In fact, we can think of it this way. This is the n equals to 3 case, and we can tag on the n equals to 4 case like this. So now you have your trigonal planar molecule from chemistry. I can't believe I'm doing that. Now, what that tells us as well, it actually tells us the answer. These are all the different isomorphic trees, right? In terms of number of trees, so we'll say n, 1, 2, 3, 4, number of trees, number of isomorphic trees, number of trees after you count isomorphism, I mean. This actually tells us that in each of the first situations, you get exactly 1 tree in terms of isomorphisms. But for n equals to 4, you're going to get 2 trees. You're going to get 2 trees. And now, how many trees do we actually have with the labeled vertices? Well, that's going to be, if we have only 1 vertex, then there's only 1 labeling. If there's only 1 vertex, there's 1 labeling. That's just 1. If there are 2 vertices, then we can use the strategy we did just now. It will be 2 factorial over 2 because you can go this way and this way and they give you the same graph. So dividing by 2 gets rid of the repetition, which is again 1 exact labeling. Now for n equals to 3, it's actually not as convenient. It's going to be 3 factorial over 2, which simplifies to 3. And for 4 labelings, this is where the fun begins, right? You have graphs that look like this and graphs that look like this. Each of them will have a certain number of labelings. So for this one, it's going to be a straight line. We're going to get 4 factorial over 2, so that's 12. But over here, we're going to get this, well, trigonal planar shape. I don't know how to describe this, but it is what it is. Or almost like a fidget spinner. And what's the idea here? The idea is we'll let the first guy be 1. We'll let the center guy be 1. And no matter how you place 2, 3, and 4, no matter how you rotate them and flip them around, you're going to get the same number of permutations. Well, and by that I mean you get the same shape. You actually get this, not even the same shape, you get the same graph, right? So 1, let's instead do 3 and 2 and 4. It's the same graph. 1 is connected to the exact same items. And so the real number of differences is the number of choices on this vertex. We can choose among 4 different vertices. So therefore we get 12 from the initial situation plus the 4 to get you 16 different labeled graphs that are trees. So it's a little bit tricky, but it is entirely doable. It's entirely doable to draw the isomorphic graphs. I think last time around we drew a few isomorphic graphs as well. Trees definitely have some better behaviors for our purposes. And we even have some really nice formulas about trees. So stay tuned for that. It's really, really cool. Now, here's a question. But before we come to this question, I want to solve another question. I don't know why I didn't type this. But here's a quick claim. And we are going to use this all the time. We'll let G be an undirected graph And we'll suppose that G is not cyclic. Let's suppose that G is not a cyclic graph. We call this an acyclic graph, but I'm okay with just using not cyclic here. Let H be a connected component of G. Claim is that G is a tree. Well, not G is a tree, apologies. H has to be a tree. In other words, if H is a connected component of G, in fact, we don't even need connected component, a connected subgraph. Let H be a connected subgraph of G, then H must be a tree. So the idea is if your big object is not cyclic, then any small object that's connected is probably not cyclic either. If the big thing, think of it this way, if the big thing has no cycle, then the little graphs also must have no cycle. But if it's in addition, if in addition it does not have a cycle, which means it's not cyclic, and it's connected, that makes the object on the inside a tree. So here's the proof. Right? So here's the proof. Since G is acyclic and H is a subgraph of G, H must be acyclic. I'm gonna let you check this result. I'm gonna let you check this result on your own. It basically means, well, on the contrary, if H has a cycle, then G also has a cycle. That's a contradiction, but essentially that's the idea. If G does not have a cycle, then H as well does not have a cycle either. And what that tells us is that since H is connected, that's what we're given here. Since H is connected, we can conclude that, and it is also acyclic, aka it has no cycle. H is a tree. Right? So it's a short proof, but we're going to use this argument pretty much like for the rest of the notion on trees. So you might want to take note of this argument, which I think you need to reproduce it. But for the purpose of this live stream, I've proved it once. I'm not going to prove it again. Right? And so we can go ahead to prove some really, really fascinating results about trees. Here's the first one. If we have a graph that is not cyclic, then we get a way to describe trees. So what do we mean by characterizing trees? So if G is a tree, then this must hold. And if this must hold, then we can tell that G is a tree. But that raises a question, what exactly do we mean by this expression? What we mean is this. For any vertex U and V, say U and V, if they are not connected in the original graph, say like this, if they're not connected this way, then when we, lots of Karens out there just making a noise, it's ridiculous. Then, if we connect them, we'll get a cycle. What do I mean by that? Here's the picture. So if G is a tree, a bit like this, G is a tree, and here's U and V. The idea being that if U and V do not have any edge connecting them in the beginning, and we do connect them, we obtain a cycle. So sort of like trees really are the extreme situation of a connected graph in a sense, right? A connected graph that is not cyclic is a tree. In some sense, you can only have a certain number of edges. If you add any more edges to it, you're gonna get a cycle, right? So I think this is called the maximal acyclic graph. So among all graphs that are not cyclic, the tree is pretty much as large as you can get. That's the idea, right? So here's the picture, and let's leave this picture here because this is actually a really, really useful picture for our purposes. Let's go ahead to prove this claim. We'll suppose that G is a tree, which tells us that G is connected. So G is connected, and what can we do if G is connected? Well, we need to try to establish this claim. We need to try to show that whenever U and V are not initially connected, connecting them creates a cycle. And by connected, I mean directly connected, right? They are definitely indirectly connected this way, but directly, that's the idea. So, what's our approach? We will attempt to prove this claim. So we're gonna fix U and V inside the vertex set, and we will suppose that U and V are not directly connected in the graph. That tells us, even if they're not directly connected, we know that G is connected, right? So since G is connected, there exists some path from U to V, and it's not a direct path, so it must meet some other person in the middle. We call them W. And this path is between U and V. So it looks a little bit like this, right? A bit like this. U goes to W, goes to V. Then we can check, and I'm gonna leave you guys to check that the cycle by connecting UV like this. Okay, so U to V to W. Well, oops, awkward. U to W to V to U. This cycle is a subgraph of this expression of this graph here of V of G, E of G union UV. And since the cycle is a subgraph of this new graph, we can conclude that this graph is cyclic, because we can find a cycle, right? We can find a cycle, right? We can find a cycle. So that's the idea over there. So that's how we show that if G is a tree, then we get that this claim must be true, that no matter which vertex you want, as if they are not initially connected directly, then if you connect them, you'll get a cycle. Now, strictly speaking, I did not consider the case when you create a loop, right? You could create a loop and get a cycle that way, and become cyclic as well. So I am again making the assumption that U is not equals to V. If U equals to V, I'll leave you guys to check this out. Okay, then you can basically create a loop. And if you can create a loop, you're good to go. Alright, so that's the first part. And now let's go to the next part of the proof, which requires us to go in the other direction. So now on the other hand, we're gonna suppose the left-hand side. In other words, suppose that no matter which two vertices you choose, if they are not directly connected, then this guy is cyclic. Right? So the idea being that suppose you have this property that no matter which 2 points you want, connecting them will create a cycle. The idea here is that we're gonna try to show, our goal is to show that G is a tree. Now we already know that G is not cyclic. So what that tells us is that in order to get this goal, we need to show that G is connected. And the reason why is because G is acyclic. So now we need to try to show that G is connected. How do we do that? Let's unpack the definition of connectedness. We'll fix 2 points. Let's use X and Y. And we want to try to find a path between them. So our goal, find a path between X and Y. That's the goal. We want to try to find a path between X and Y. With that goal in mind, how do we start? Well, we need to ask the question. Either we have a path directly or not, right? Either we have a path directly or not. So either xy lies inside E of G, or x of y does not lie inside E of G. Now, if xy lies inside EG, we're getting a situation that looks like this. We have a path, right? So then xy is a path between x and y in G. And we're done. And that's it. However, we still need to consider a situation when xy does not lie inside EG. And what that means is, okay, how do we continue from here? Well, we know that x and y are vertices. We do know they're vertices. So, if they are not directly connected in G, we get this property for free. We must get, by the assumption, by hypothesis, that this graph must be cyclic. Now, the problem with it being cyclic is that we know nothing about this cycle, right? So, let's just say it contains some cycle. Let's call it C. Let's call this cycle C. And at this point in time, it's like, okay, how do we proceed? How do we proceed from here? Well, the idea sort of is to ask this question, right? Is roughly speaking to repeat this question, right? Now we are looking at a situation when we have not u and v here, but we have x and y. And the idea is sort of, oh, by the way, once again, I'm working with the situation when x is not equals to y. If x equals to y, exercise, right? If x equals to y, I'll let you guys check that we either get by one or contradiction. So, the idea is sort of like leveraging this, right? We want to show that the cycle contains x and y, one way or another. But how do we even approach that, right? So we have two cases, right? C does not contain xy versus or C contains xy. Now, if C does not contain xy, then you can check, and I'm gonna let you guys check this out, that C is a subgraph of G. And if C is a subgraph of G, in other words, the non-modified graph, then we must have that G is cyclic. But if G is cyclic, that's a contradiction because why is it a contradiction? We contradict the assumption that G is not cyclic. Right? We made the assumption here that G is not cyclic. And so that's a contradiction right there. So this tells us that C must contain xy. Now what it means is that we can write it this way. Oops. We can write C. Okay, so write C as the path x to w to y to x. Alright, write this path. But that tells us that if we were to just consider, well, the picture looks a bit like this, right? If we were to connect xy, then we get a cycle, and this cycle will pass through some other point w. But that means we can take this path. So this tells us that x to w to y is a path between x and y in G. Right? X and xwy has to be a path in the original graph. But what does that mean? If you can find a path between x and y, then that tells us that we can find a path between x and y, which tells us that G is connected. And if that tells us that G is connected, that tells us that G must be a tree. And that's a really, really interesting proof, I have to say. I do find it to be a rather strange and fascinating proof. And it works really nicely. Okay. So that's one of the first results on trees. Now, once again, as long as there is that one result which we kept using. If you have a connected subgraph of an acyclic graph, you get a tree. Okay, so let's take a look at this. This is what we call the tree formula. I call this a tree formula. It's a really, really famous formula talking about the number of edges and the number of vertices in a tree. So we let G be a finite and undirected graph. Then, if G is a tree, we're going to get this neat result. And how are we going to prove this result? We're going to use what my good friend Eugene, he calls this the induction hack, the graph theory hack, if you would. And the hack, as the name suggests, involves induction. So we're going to prove this by induction. So we'll prove by induction on n. But what is n? Usually what we mean by n is the number of vertices of the graph. So let's start off with the base case. Let's start off with the base case n equals to 1, because we insist that it has at least one vertex. So the base case n equals to 1 would tell us that, G looks, okay, so G, here's G as a tree. G looks like this, right? So this is the graph that represents G. Clearly it has no edges, right? G is a single vertex. It has no edges because it's acyclic. If it does contain an edge, then you're going to get a loop. And clearly that's problematic. So the number of edges is going to be 0, but this is equal to 1 minus 1, which is the number of vertices of G minus 1. Okay, so what are we going to do from here? Okay, this is where we're going to get a really, really interesting result over here. So suppose result is true for Vg equals to 1, 2, all the way to k, right? And now we'll suppose that Vg is equal to k plus 1. So what's the picture that we have in mind? Okay, I'm going to draw the situation when we have 6 vertices here. And the idea is that we could chop off one of the edges. And once we chop off one of the edges, we are left with 2 connected parts, connected components. These connected components do not have cycles, so that means these guys are trees. And then we can slap on the induction formula. Right? We can slap on the tree formula using induction. So that's the sort of the idea here. So suppose Vg is equal to k plus 1. Okay, we'll let uv be an edge inside the graph. We'll just let uv be an edge inside the graph, right? So a bit like this. Now it could be somewhere else, but we need to let uv be an edge inside the graph, right? It could be any 2 points, but it is that. Then the idea is that if we were to cut off this guy, then we're going to get 2 connected components on their own. Okay, so here's the idea. We'll define H prime to be all of the vertices in G, right? But one less edge. But we're going to chop off UV. We're going to get rid of UV from this tree. Let's chop it off. Right? Now, what remains is basically the part connecting U and the part containing V. That's basically it. Correct? So we can define HU and HV to be the connected components of G that contain U and V respectively. And I am going to let you check, and this is slightly tedious of an argument. Maybe we should check it. Okay, so let's just first claim let's just make a small claim here, that the vertices of HU and the vertices of HV will give us the vertices of G, right? And furthermore, in fact, the vertices of H prime and then the edges of HU union the edges of HV is going to give us the edges of H prime. Now I'm just going to claim this first. I think we'll prove it because it does take a little bit of effort, but I think it's not too bad. Once again, we could probably use something like the eating up lemma from the previous stream. And what we're going to do here is, once we can satisfy this claim, what we have here is that since the number of vertices in HU excludes V. Whether it excludes anything else, we don't know, but it must exclude V, so it must be smaller than K. And the number of vertices in HV excludes U, so it has to have at most K vertices. We can slap on the induction hypothesis. Oh, by the way, over here we're also claiming that the union is disjoint. Right, we're also claiming that the intersection here is a disjoint intersection. So that's rather fascinating as well. Okay. So if that is the situation, we can slap on the induction hypothesis. Right, so by induction, okay, to be more precise, we need to check that it's a tree as well. So let me give you guys a quick claim. Okay, so let's just quickly establish this result. So we'll come back to this in a moment. Now, since HU and HV are connected subgraphs of G, which is acyclic, G has no is assumed to be a tree, therefore it's acyclic. This tells us that HU and HV are trees. And if HU and HV are trees, then if you consider the number of vertices of each component, we can slap on the induction hypothesis to get E of HU equals to V of HU minus 1 and E of HV equals to V of HV minus 1. So the idea being that, here's the whole idea. Since this guy is a tree and this guy is a tree, we can slap on the induction hypothesis. We can slap on the inductions over there. And this tells us that the number of edges in E of G is actually equal to the sum of the edges in HU and the sum of, or rather the number of edges in HU plus the number of edges in HV plus the edge UV, right? Plus the edge UV. So that's plus 1 over there. We can plug in E of HU. Let's plug in E of HU. Let's plug in E of HV. And let's plug in a 1, or just the initial 1. Some terms cancel out, as we can see. The ones will cancel out. We are left with VHU plus VHV minus 1. But that will simplify because VHU and VHV give us VH prime. And VH prime is actually the same as VG. This will equal to VH prime minus 1, which is VG minus 1. And we are almost done. We're almost done, and the reason why is because we actually haven't proven this claim just yet. So let's go ahead to prove this claim, and then we'll go for a short break where I need to set up some stuff on my side. So now let's make this claim according to this definition over here. We are given that G is a tree, and we now make these claims. Right, So let's just very quickly prove this result. Takes a bit of effort, but it's fine, right? So we call that G excludes U and V, right? So these are the two claims. Here's the proof, right? The proof is that, well, what do we mean by VHU and VHV? Again, here's the picture. So we'll call this U, and we'll call this one V. Looks a bit like this, right? So how do we show that that's the situation? Now, it is pretty straightforward to prove this direction. And to prove in the other direction, we'll fix some vertex x inside V of H prime. And what do we know here? Well, we do know that x lies inside well, V of H prime, okay, so how do we sort of continue from here? Okay, let's do it slightly differently. Okay, let's first check that this must be empty, right? So we'll suppose there exists some other guy that lies inside V of HU and V of HV. This tells us that HU and HV contain W. However, the connected component, there exists a unique connected component HW that contains W. So let me rephrase that properly. And it contains W. And this connected component must be unique. This tells us that HU equals to HV equals to H of W, which tells us that U lies inside the connected component of V. And that tells us that there exists a path from U to V. I can see why this might take a bit of effort. Since UV does not belong inside the edge set of H prime, because we define H prime to be the vertices and the edges excluding UV. Since UV does not belong to H prime, the path P is, well, the path between U and V has the form U to W to V, which tells us that U to W to V, U lies inside the original graph G, well, lies inside, is a subgraph of G. And if this is a subgraph of G, this tells us that G is cyclic, which is a contradiction. All of that is to say that the vertex sets must be empty. Otherwise, we're going to get a contradiction. Right? And so that's the idea over there. Now, we've actually only proven one claim here. We need to prove a few more claims. So let's go ahead to do just that. So that's the first claim. Takes a bit of effort, but roughly speaking, we try to derive contradictions so we can take advantage of there being a cycle and whatnot. Now, I believe these two ways are pretty straightforward, but we need to prove in the other direction, right? So we'll need to prove, we need to prove in this direction, So we're going to take any vertex x inside V of H prime. And what we do know is that x, there exists a unique connected component, Hx, that contains x. Right, that's the sort of the idea over here. And well, how do we make the case? How do we make the case here? The idea sort of, there is one other approach, and feel free to raise your own approaches which work, is that if you can find another guy X that looks a bit like this, then even if you were to connect UV, this X is going to be totally isolated from everybody else. So here's the argument. Suppose X does not lie inside VHU or VHV. Then, right, G has at least 3 connected components, HU, HV, HX. At least 3 distinct connected components, where we do know that X is inside. We do know that X is inside X, that HX contains X. That's definitely going to be the case. So we might need to do a bit of effort to show this guy. I think this can be done because if you show that it has less than or equals to 2, you get a contradiction. So here's an exercise for you. Try to show by contradiction that G has at least these 3 distinct connected components. This tells us that the edge set, right, or rather this is not G, but this is more precisely this H prime. This tells us that if we were to connect back U and V, right, G must have at least 2 connected components that are distinct. Right, and over here, there's a little bit of effort again. Once again, you can try to show proof by contradiction, right here, right, that if G has at most 1 connected component, then X is connected to everyone, and then therefore X lies inside the vertex set, which is a contradiction. All right, so that is the idea here. In fact, we might be able to make a clearer claim over there. But it's okay, you can try to argue the case, right? Once you've argued the case, you have shown that we get this property as well. We get the same property as before. And we have to just repeat the same argument for the other situations. Now let me see if you can make the claim. Now I'm gonna let you guys check these on your own, okay? I'm gonna let you guys check these 2 claims on your own. The argument is going to be pretty much the same as before, right? The idea is that if an edge exists, then HV and HV are connected and all hell breaks loose. If you can find an edge that does not belong in the complete, if you can find an edge here that does not belong to the union here, again, all hell breaks loose because if that were to be the case, then you're going to get too many connected components, and then the original guy cannot be connected. So the argument is going to be the same, and feel free to make the case, right? Feel free to make the case. Yes, I think the argument works because we're working with connected components. Connected components is a really, really strong object in graph theory, so I think we can make the claim over there. Actually, this might take a little bit more effort than I thought. Alright? Okay, I think we need to prove these guys as well. I think these are not very straightforward results. The strategy is there. We sort of have some idea to go about it. Okay, by the way, we need to finish this argument here. G has at least 2 distinct connected components, therefore G is not connected. Contradiction. Right? Now I think we need to do a little bit of effort to prove these two results over here. So let's try and see how we can go about it. So we'll take an edge RS inside. Okay, so we'll suppose okay, so let's suppose there exists an edge RS inside EHU intersect EHV. This tells us that, well, R belongs to HU, S belongs to, well, R and S, they both belong to HU, well, VHU, and VHV. It belongs to both actually, right? But once we get that, then we have shown that this is non-empty, right? So that means this implies this, which means that VHU intersect VHV is non-empty. Contradiction. We get a contradiction. Okay, so that was not too bad. And finally, we need to go in this direction. So we'll suppose there exists, not suppose, let's fix RS inside the edge set of H prime. This tells us that R lies inside V of H prime, and so same conclusion for S. We get R and S lying inside V of H prime. And then what can we derive here? Well, we can derive that one of four cases. We can split this up into four cases. Right? Either R lies inside VHU and S lies inside VHV, or R lies inside VHU, S lies inside VHU, R lies inside VHV, and you can check the others. You can check the other few cases. In fact, I'm just gonna do it this way. So let's just do it like that. Okay, we might be able to do something a bit interesting. So suppose, without loss of generality, that R belongs to HU, right? VHU. You can prove the same thing with VHV. So, what on earth are we going to do? Well, since R belongs to the connected component HU, since R belongs to the connected component HU, we can draw this picture like this. This is HU, and S goes into R, right? We have a path, right? So by the eating up lemma from the previous stream, RS will lie inside the edge set of HU, which lies inside the union of the edge sets. And I think the previous argument would have been, I feel like we could use the eating up lemma to clean up the previous argument. Now, of course, that is suppose R lies inside VHU, right? And is it possible that, oh wait, we might be a little bit, there might be a little bit of a problem here. Oh, no problem, because we've already proved this. So actually, we needed to prove this sort of from scratch, but once we have this, we can now assume this, because VH prime is, by the first claim, VHU or VHV. So now we can assume that this holds, and suppose R belongs to VHV, you can complete the argument, which is basically isomorphic, if you would. It's an isomorphic argument. So finally, that establishes this last claim. Now we've claimed all these things, we can now formally, more properly, go back to the tree formula, and finally this claim is met, which tells us that HU and HV are connected subgraphs of G, and therefore they're acyclic, and they are trees. And because of this, we can use the counting techniques to obtain our tree formula via induction. All right. And with that, we'll go for a short 5-minute break. I need to set up my system here. As you can tell, I'm not in the usual room. I'm actually outside, and we'll be back in just a moment. All right, welcome back to the stream, and we are going to continue with trees. So we've actually proved the tree formula, really powerful result here. And we have a few variants to the tree formula. We're going to use pretty much the same strategy. What we did here is that we cut off an edge to obtain 2 new trees. That's the key idea. We cut off an edge to obtain a bunch of trees, and then we argued from there. We're going to use that same idea for the 2 other results that await us. Okay, so we had to prove some lemmas along the way, but those are just stepping stones for what we need to prove. So here's the question. If G is connected and cyclic, then we get a strict inequality. If it's acyclic, in other words, it's not cyclic, then we get a tree and we get equality, right? So here's the claim. Now once again, let's prove the claim. We will prove by induction on the vertices of G. So for n equals to 1, we are gonna have, well, Vg equals to some vertex. But we know that G is cyclic. That's the assumption, right? G is cyclic. So since G is cyclic, there exists the loop. Because you only have one vertex, the only cycle that could arise is a loop, right? Inside the edge set of G. And this tells us that the number of edges in G is 1. But this is strictly bigger than 1 minus 1 because 1 minus 1 is 0, so 1 is bigger than 0. But that's your vertices of G minus 1. That's the case for n equals to 1. Now let's go with the induction hypothesis. Suppose true for n equals to 1, 2, all the way to k. Then suppose now our new graph has k plus 1 vertices, right? Induction goes from, okay, suppose it's true for all of the smaller graphs. Now consider this graph, we want this eventually to be true. And yes, we're using strong induction, so that's a subtle difference there. Why do we use strong induction? Because this gives us more weapons to work with. That's all, right? It gives us more weapons. So, suppose the number of vertices is k plus 1. What does that tell us? Well, here's the picture, right? We know that G is cyclic, right? So since G is cyclic, it contains a cycle C. And we can draw the picture a bit like this, right? So you can either have a cycle that looks like this, and then you have everything else, which is all connected, right? You could have multiple cycles, right? But I think this should be enough for our purposes. You could have a loop as well, but it's interesting, we don't actually have to do any distinguishing on whether it's a loop or not. So what's the trick over here, right? So, well, there is actually one situation we have to consider. It could be the case that the entire graph is a single cycle. We could get a graph that is a single cycle. So we have two cases to consider, right? So our goal is to show this result, right? Let's maybe clean up the base case and then we'll continue with the induction. Let's put in the pictures, and these pictures may or may not come in handy for our purposes. And so, suppose G is a cycle. Suppose the vertices of C is the vertices of G. In other words, we get this situation. Then, what are the edges in C? Well, the edges in C are going to be each of the connections. And the number of connections is precisely the number of vertices of C. Right? In a cycle like this, you are definitely going to have, where were we? Gosh. You're definitely going to have these cycles. And, or rather, in this cycle, the number of edges is the number of vertices. So this is clearly going to be strictly bigger than the number of vertices minus 1. But if the cycle is V of G, that tells us that if the cycle is the graph is the cycle, then we can replace C with G to get E of G bigger than V of C minus 1. So clearly, this is case number 1. If the entire graph, right, is just a cycle, then we have to consider this possibility. But it could be that it's not just a cycle, right? In other words, suppose, case number 2, that VG excluding VC equals to, or rather, is non-empty. I suppose VG excluding VC is non-empty. That tells you that you can find some U. Okay, so and since uh, so there exists some u inside v of g excluding v of c. Roughly speaking, this portion over here, right? So there is this guy over here. The idea is we're going to chop this off and we're going to apply induction here and here. That's sort of the idea that we have. We're going to chop this off and then apply induction. So what are we going to do here? So what do we have here? Okay, so let's do it this way. So suppose this is non-empty, then for any u inside the cycle and v outside the cycle, there exists a path u all the way to w to v between u and v. And the reason why is because G is connected. Right? We will let W denote the first vertex outside of C, right? And we might need to check this later. So we claim this is legit. We'll probably need to use some well-ordering principle argument to do that, right? But roughly speaking, here's the idea. If you start from U, you have to, if you start from U and you go to V, you have to pass through basically the strait, if you would, between the cycle and everything outside of the cycle, right? And the idea is we're going to chop this up. We're going to chop this up. Define H prime to be V of G, still everything, but now we're going to consider all of the edges excluding, we might need to do a bit of work here. So let W denote the first vertex outside of C, and we'll call Z denote the last vertex inside of C. And we're gonna very quickly show that this is legit in just a moment. Okay, we're gonna prove that this will be legit. Now, what's our goal again? Our goal is to eventually prove this inequality. We need to prove this inequality. Let me maybe zoom out a little bit. Reduce the size there. Let's create a bit more space. And so what that tells us is that if we want to try to prove this inequality, we're gonna have to do a bit of work. Well, what work do we need to do? Well, we're gonna define H prime to be the graph VG EG excluding WZ. Okay, here's the idea. So the idea is we're gonna chop this up over here. Okay, so now we can check, and I'm gonna leave you guys to check this time around. We're gonna check that V of C, right, union V of everything else. Well, this will give us V of G. I think this is pretty obvious, right? But more precisely, we can strengthen the argument here. V of C union the connected component containing W. This is going to be everything. I'm going to let you check this because the argument is going to be exactly the same as before. It's going to be the same argument that we did previously, right? So secondly, E of C union E of HW is going to be the edges of G. Let me take a look. Let me just take a look and see if the argument actually follows along. Okay, this argument is slightly problematic. We actually have a subtle difficulty over here. I think we can still make the claim, but it does take a little bit more effort. Um, I think you can contradict it in a slightly different way. So I will still let you guys check this on your own. Right, so the idea being that if it is connected, we're actually going to get more edges than we're supposed to. Or rather, if it's connected, then actually this might be a bit troublesome. Now I think about it. Now that I think about this argument a little bit more carefully, because I have missed out a really important situation. I've missed out the situation that this could be a cycle as well. And if I would just cut this out, we're still gonna get something that's connected. So, I think you could try to make the case that either it's connected. Oh, okay. I think this is fine. Okay, so, oh gosh. Okay, let me think about this. Okay, so there exists a path UV. Okay. Okay, I think we can make this argument a little bit more airtight. So let's go. Let's do this. Okay, so we're still gonna define it this way, and we can still we can still define H prime in this manner, but we do need to consider two situations. Case number one, right? Case number one, a sub case if you would. H prime is connected. Well, this is not very convenient. Okay, looks like we need to do a little bit of work over here. Okay, so let me redo this induction argument over here. Okay, I remember there was another argument I used which was really, really powerful. So here's the idea. Okay, so suppose in case number 2, we'll suppose that Vg excluding Vc is non-empty. Right, it's going to be non-empty. Well, the idea is that if it's cyclic, we can sort of capture all of the different cycles inside the graph, right? So what do I mean by that? What I mean is that you could have one cycle, you could have 2 cycles, you could have as many cycles as you want, right? You could have as many cycles, right? And then and you could have cycles that even sort of combine, right? You could have a cycle that looks a bit like this, and then you have a cycle that looks a bit like this. So you have all of these cycles, and now what that tells us is that we have 2 situations, right? Right, we have actually 2 situations to deal with here, right? Okay, I think I have another, I have an even better idea over here. Okay, I think I have an even better idea. So here's my sort of the idea that I have in mind. Now we have a cycle here. We sort of have a cycle, right? And then this cycle, it may be the only one, it may not be the only one, right? But then the idea is sort of to take this cycle, right? And this cycle is going to look a bit like this, right? If we were to chop off one item. So in other words, if we were to chop off an edge, right? Ideally, we're still going to get everything else is still going to be relatively connected to one another, no matter which edge we choose, because within the cycle, if you were to chop off an edge, you're still going to get another path, right? If you have a cycle, you chop off an edge, you're still going to get a cycle within the other path. And what that tells us is that we could be able to apply some induction argument over here. But I need to think of how to make this a bit more rigorously airtight. Okay. Perhaps let's not use this idea. Let's use the cycles idea, right? So we have a few different cycles. Perhaps it looks a bit like this. Sometimes the cycles may have a direct overlap like this as well, right? So what we'll do is we'll let C1 to CK denote the cycles in G, right? And we could have cycles that even look like this, right? That's possible. We could have cycles that look a bit like this, but cycles that look like this is isomorphic to this, so this is fine. We don't have to worry so much. Okay, so suppose let's C1 to CK. Well, let's not use CK. We've used K. Let's replace it with CM. Let's C1 to CM denote all of the cycles, right? So the idea is this: either every point lies in a cycle, or there is someone that is actually not contained in any of these cycles. You get what I mean? So that's the idea. Either any point you pick will lie inside the cycle, or it's going to just lie on the outside. So here's the two sub cases. So sub case A, for any vertex, say V belongs to Ci for some I, and alternatively, you have the other situation when you might have some vertex such that V does not belong to any cycle. Okay, so that's the idea. That's the idea that I have here in the moment, right? So if the first instance is the case here, if we get the first instance, then we can try to sort of get rid of a point, or rather get rid of an edge, and then apply some induction argument on it. Now, what might be a bit interesting here is that if V belongs to Ci for some I equals to 1 to M, then my idea is to sort of just apply induction on the cycles themselves, right? We could apply induction on the cycles themselves. So I think that's what we're going to do. So for A, okay, so part A, then what this means is that vertices of G is equal to the union of the vertices of Ci's, right? And then what we have here is that each V of Ci has to be smaller than or equals to K, because there's more than one Ci because of this result here, right? Because the graph is not just a single cycle. It's actually made up of multiple cycles, so each of these cycles must exclude at least one point. So each of them has size less than or equals to K, which allows us to apply induction. By induction, here's something really interesting. The edges of the graph will contain the edges in each cycle. Clearly, it may have more, it may have less, we don't know, and honestly, we don't really care, but it has to at least contain the edges in the cycle. That makes sense, right? Because EG will be a superset of E of the Ci's. Each of the Ci's are subgraphs of G. And that tells us, right, so this would help us obtain, okay, this might be a problem, give me a moment. Okay, so I realized that there was a slight problem in my argument here, because we might encounter a situation when we are gonna count extra CIs. So this is kind of awkward and embarrassing. I need to fix this bug one way or another. Now the idea is sort of, okay, if this happens, then we can just take the bigger cycle. That's really the idea that I have here. Right? So okay, so we're gonna define it this way. We'll let C1 denote the cycles in G with that do not have any common edge. This is possible, right? Because if we do have a common edge, just cut it out. Right? You cut it out, you're still gonna get a cycle. So that's the idea. Right? Yeah, if you cut it out, you're still gonna get an edge. Yeah, suppose you have the cycles and they don't share a common edge together. You can make this situation. This allows us to bound the number of edges above by this inequality, right? Bound it below by this inequality, and we can write each of these guys using the induction hypothesis. Each of these guys are connected cycles. These are all cycles, so we can upper bound this by the sum of I equals to 1 to m of v of ci minus 1. And this is very bad because we get a very raw upper bound. We actually get a very, very raw upper bound. We get a very, very raw upper bound because we're only getting the summation VCI minus M. Right? So that's the only one we're getting. This inequality. So this is not a good strategy. This is a very bad strategy. Let's not use this particular argument here. Okay, let's not use this argument. Okay, so let's go this way. All right, let's modify the argument, right? And then we'll fix x inside v of c1, right? So it'll be inside the first cycle, and we don't have any common edge. Okay, so we'll do it this way. So we'll fix xy inside the edges of C1, and what this tells us is that C1 is not going to have any common edge with all of the other cycles, correct? So okay, I think we have an idea here, right? We have some idea of how to go about it. Okay, this might be a problem. Oh gosh. I think we got something. I actually proved the result, which was pretty strong. So okay. I think we got something here. Now recall over here, right? So once again from part A, right? So suppose that we get a case when this whole thing is just made up of cycles. Okay, it looks a bit like this. Sometimes they overlap. So the idea is that the total number of edges has to contain the total number of edges in the cycles. Correct? It has to contain it. In fact, I don't think we don't need to impose this. I don't think we need to impose. Oh no, I think we're gonna still impose this. We're still gonna impose this. Yeah, okay. But once we have that, then we might have a problem. Okay, scratch that. Oh gosh, this is awkward and embarrassing. Give me a moment. Let me sort of recollect. Because the problem is that these guys here actually do intersect. They can intersect. Right, so that is actually the problem here. Okay, let's just start from this point over here. And let's try to just work some magic here. So suppose you have a cycle. Here's a cycle C. And you have some point that does not connect to the cycle. So then we'll let U be the element inside V of G excluding V of C. Now the reason why I was so troubled, right, is that I was thinking to myself, wait, you know, what if, right, there could be another path that looks like this. There could be some paths that look like this, or perhaps look like this. So let me explain. So here's the cycle. Well, so here's the point U. Here's the cycle C. Right? It could be the case that U could be connected to C, but via a cycle. Okay? But it could be connected to C through a cycle. So I think here's how we can make the case. We're gonna chop off every single possible path that goes from U to C. Okay, but what do we mean by that? Okay, so here's how we're going to describe it. We're going to define it formally this way. We'll define V of H prime, or rather we'll define H prime to be the vertices in C, or rather we'll define it this way. We'll define a particular collection of edges to be of the form XU. But each of these XUs are defined by X belonging into the cycle. Okay, X belonging into the cycle like this, right? Okay, and okay. No, we need to define this very, very properly. Okay, so there's quite a bit of work to do. Okay, but let me just show the general picture. If you can create a U here, you can create a path like this, and then you can find the first guy, say V, such that it attaches to U, right? That goes all the way to U, right? So here's what we do. Okay, so since G is connected, there exists a path from any point in C to U. Okay, and so we're going to basically say we're gonna call this point W to U, right? So you can find a path, right? And then for each path P, we'll let VP be the first vertex, right? We'll let VP be the first vertex that lies inside the that does not lie inside the cycle. Okay, so that's the idea. Right, now this one I believe we can actually check this out. We can check this using some induction ideas. Did we prove it just now? Okay. Yeah. I think we can prove this later on using some well ordering principle, most likely. Okay. So for each vertex, for each path P, let VP be the first vertex that does not lie inside C. So in other words, from W to U, you can have a bunch of different paths, right? So for all of these different paths, we're going to let VP be the first guy that lies outside of the cycle. So you have a bunch of VPs here. These are all VPs. Then, right, we're going to define E sub U to be the collection of VWs such that the collection of VPWs, where P is a path between W and U. Right, and here we're gonna just assume from W to U, just so that we can define VP in a relatively convenient way. Right? So the idea is that we're sort of gonna cut off access, right? From U, we're gonna cut access off from no matter what you want to connect towards U, no matter how you're gonna connect towards U, we're gonna consider the first guy, and then we're gonna basically chop off all of these edges. We're gonna chop it all off, right? So now we can define H prime to be still the same collection of vertices, but now you have that E, you have E of G excluding these particular edges. We're gonna chop off all of these particular edges, right? And you can actually check that, and you can, here's a claim, that H prime, okay, right, that V of G is equal to, or rather H prime, the claim is that H prime equals to the connected component containing U. That's not correct. Sorry. Give me a moment. The claim is that the edges in HU union the edges in the cycle will give us H prime, right? So the idea is that we can combine all of these to form HU, right? And then of course the union is a disjoint union, right? Where HU is a connected component of U inside H prime, right? So the idea is you sort of connect all of these other guys, and then you form this all as a single connected component. And this is a legit idea. Yes, this will be legit. This should be legit, unless U is directly connected, in which we get a problem. Oh gosh, this is so irritating. Okay. Oh no, that's fine. We're just getting rid of the edges. We're not getting rid of any vertices, so that's fine. Okay, I think this works. Yes, this works. So we can check. Okay, so we claim that we have this. Well, this is awkward. We claim that this is going to give us the connected components. Right. So the idea is that, well, if we were to take this guy and this guy, this will give us all of the edges inside H prime, where we get rid of the bridges. We get rid of every single bridge from the cycle to U. I think we need to be more precise here. Technically, it should be any path from the cycle to U, right? So from any W in VC to U. Okay. W in POC. There we go. I think this is more correct. So this way, no matter what you do, U will always be cut off from the cycle. Now the interesting thing is, because of the fact that these paths exist, we're going to get connectedness. So I'm gonna let you check this claim. It will take a little bit of effort, right? It will take a bit of effort because, the idea is there, right? So you have the edges here, and then you have the connected component, and this gives you everything except the things that you chopped off, right? So I'm gonna let you check this, although it does take a bit of effort over there. I'll probably do this later on at the end of the stream as well, just to maintain some sanity. So we'll probably KIV this claim over here. Okay, I think this is true, but if we do have this claim, and I'm probably gonna have to prove this later because it actually looks quite difficult to prove. If we do have this claim, then essentially, right, we have this, right? Since the number of vertices of HU is small or equals to K, and the number of vertices in the cycle is smaller than or equals to K, by induction, right? Okay, we have to be a bit careful here. So, firstly, if the number of vertices in the cycle is less than or equals to K, so let's just do that first. Since C is a cycle, therefore it's cyclic, we have that the number of edges is going to be equal to the number of vertices. In fact, it's going to be strictly bigger than -1. This is going to be by induction. By induction, we're going to get this property. Now, what about the other part, right? So the idea is we can split this up into C and the connected component containing U. Now, here's the problem, right? We know that just like if the number of vertices in C is smaller than or equals to K, the number of vertices in HU has to be smaller than or equals to K as well, right? The idea is that if everything is K plus 1 and you get rid of at least one item, you're only left with at most K items. But here's the thing. We have two situations. We actually don't know whether HU is cyclic or not. We actually don't know whether it is cyclic, right? We do know that we have chopped this part off from this cycle. The way I draw it here, it looks like it's not cyclic. But again, you could have another cycle here. So what do? Now the beautiful thing about induction is that you don't have to worry so much. Because if HU is cyclic, in the set case that it is cyclic, well, it's connected and cyclic. Because it's a connected component, right? So if it's connected and it's cyclic, tells us then we can apply induction to obtain that the number of edges in HU is bigger than the number of vertices in HU minus 1. So that is entirely possible for our purposes there. And if it's acyclic, then we have that HU is a tree. And if it's a tree, we can apply the tree formula. Right? We can apply the tree formula. And the beautiful thing is that regardless of which outcome you get, E of HU is lower bounded by VHU minus 1. It will always be lower bounded. Now, once we have that out of the way, here's where the fun begins, right? That tells us that we can now consider E of G, right? E of G is going to be equals to E of HU plus E of C plus E of EU. Well, not E of EU, but the number of items in EU. Right? We do have an EU over here. Right? We do have an EU over there. Of course, we're hoping that that thing over there is going to be, it has to be bigger than or equals to 0. Right? So this item here is bigger than or equals to 0. E of HU is going to be bigger than or equal to V of HU minus 1. And E of C, in fact, E of C is a really interesting case. It's going to be equals to, it will be strictly bigger, right? It will be strictly bigger than V of C plus 1. Alright? And actually, the way we define EU, right? The way we define this way, because U lies outside, we're definitely going to get at least one path. So we definitely will have at least one element over here which allows us to maybe plus another 1 right there, which is very nice. I think this is a -1. That was awkward and embarrassing. That was a -1. So stuff cancels out, and we're left with v of HU plus v of C minus 1. But once again, v of HU union v of C, again by the way we defined it, is simply going to be v of G minus 1. And that's how we prove it. Now, of course, we have some work to do, right? We actually have not actually proven this claim, and we will need to come back to this in a moment, right? In fact, maybe let's try to prove this claim right now. Let's go and prove this claim. Now, if this claim holds, we're good to go. But let's try to prove this claim right away, because I don't like to push things off to the last minute. The most important lesson that I've learned is to not procrastinate. Yeah, surprise, surprise. It's actually possible to not procrastinate. Okay, so let's try to prove this claim. Okay, and here's my attempt. Right? So I think it is all right to, well, if HU is a connector component of H prime, we're good to go. And then if C lies inside E of G and is not part of this guy, we definitely do have this inclusion over here. This would definitely hold. Now to check this side, okay, we'll fix XY inside the edges of H prime. Okay, and I think we can more or less see that, and this is the part I'll let you guys check. Then you can check that. Right, you can either check that they must belong to the same component, right? Right, they have to belong to the same, well, HU, right? They have to belong to the same component, and if they belong to the same component, you can check that in either situation, XY does not belong to E of U, right? And this also means that XY does not belong to E of U. You can check these two claims yourself. So I'm gonna leave you guys to verify these on your own. Right? This part should be pretty alright to check. You can try a contradiction argument that's pretty useful as well. Okay, so that's that. And there is that. So based on the way we defined it, okay, wait, no, this is really, really sus. No, I'm just like not answering the question. What am I doing? Okay, so fix XY. Yes, from here you can actually check that you can use something along the lines of the eating up lemma. And you can conclude that XY must belong to E of C, or XY belongs to E of HU. That's definitely going to be the case. Yeah, you can use the eating up lemma. Yes, please use the eating up lemma. You can immediately get this pretty quickly. Yeah, right. And roughly speaking, again, it's because we do have a property that tells us that V of C union V of H prime, H of U gives us V of H prime. Right. This one is pretty alright because it either belongs into the connector component containing C, or it does not belong to the connector component containing C, and therefore it must belong to the connector component containing U. Otherwise, we'll get a contradiction. So I'll let you guys check this as well. Yeah, so we've seen some of these arguments before, and you can check that these things will hold. You can check that the eating up lemma helps you get the desired result under the assumption that C and HU really does give you the entire graph. And once you have those things in place, you're good to go. You're good to go. So, right, that's the proof claim, and I think it works. So, yeah, it works. Yeah. So, just a quick recap of how we prove this result, right? If it's connected in cyclic, then we will again use induction. For the base case, it's pretty straightforward. For the induction step, it takes a little bit more effort. Either we have this property here, where the entire graph is the cycle, which gives us the result pretty quickly, or you have some other guy which lies outside of the cycle. Then the idea is to chop off all of its possible neighbors. This itself is going to be, this is going to require some induction. This is going to require some induction as well, right? That's the big idea. Everything else is just to make sure it's legit. So we had to use this in order to chop off all of these paths. I think we actually needed to prove this. So let's very quickly prove this result right here. Let's prove this one. Okay, so for any path P, we'll denote it using x0, x1, all the way to xu. Yep, to x. We'll denote all of this to yeah, okay. Yeah, okay. This is fine. Give me a moment. Oh, I think we can define this a little bit more clearly. We don't even need VPs. I don't think we need VPs. Yeah, there's no need for VPs. So we're just gonna define it this way, and we know it's non-empty because we know we have at least one path. So here's the idea. Okay, so rather than V being a path from W to U, we're just going to chop off any connection that we can get from the cycle, say W. Okay, and in fact we don't even need W per se, right? Yeah. Oh, we can do that. So WV, we just chop it off. So in other words, whenever W lies inside the circle and V lies inside V lies outside of the circle, the cycle, we're gonna put it all into this box called EU, and we're just gonna chop it all off. That works. That works out very nicely for us. And we're good to go. And the argument still works, so we're good to go. So we chop off everything that is directly connected to the cycle. This is what we mean here. We'll define H prime to be the split version of these two guys, essentially just these edges. We can slap on induction on both of them and check that all of the conditions work. That's basically all the hard work we did. Check that this condition works. We had to prove a little bit over there. And then we can apply the induction results and get our final answer. So yes, it took a bit of effort and it's not an easy proof, so don't worry if you felt that it was a really long and arduous proof, but this is the most important picture to conclude all of that. Okay? Well, that took a bit more effort than I expected, but it's fine. Now, we have a similar result. This one takes less effort, right? So, but we're gonna basically use the exact same strategy, right? So once again, now, if G is not connected and it's not cyclic, then we can ask a related question. Can we prove this particular identity? Can we prove that this result for trees over here? Now we can, right? The answer is that we can. It works out. And here's how we're gonna do it. We're gonna prove by induction yet again. So prove by induction on B of G bigger than or equals to 2. You might be wondering why bigger than or equals to 2. Well, because if v of g has only one item, if it only has one item, then g is the graph this. And a graph with one point has to be connected. So clearly it's not going to work, which tells us that v of g has to be bigger than or equals to 2. Right, so we do it this way. So that's the way we're gonna sort of establish the claim. So our base case, if n equals to 2, my student Tisha actually came up with this proof. It's a really clever proof. She just basically listed out all of the different possible graphs. So G is one of the graphs. Right, here's, if you want acyclic graphs, you can only have either these two options because there's no cycles. And only this one is not connected. Right? It's not connected. Therefore, the number of edges has to be 0, which is smaller than 2 minus 1, which is the number of vertices minus 1. Really clever proof, really short, no need to do any contradictions and whatever. I'm all for it. Right? So, that's nice. Now let's try to prove the induction step. Right, so let's do the induction. Suppose the result is true for k equals, well, the number of vertices being 1, well, 2, 3, all the way to k. Now we're going to suppose n equals to k plus 1. In other words, the vertices of the graph is k plus 1. We're going to now make this supposition. Then, what can we derive from this? Well, since VG is not connected, right, it must have at least two connected components. But let's write it this way. There exists U and V inside V of G such that there is no path between U and V. So that's the idea, right? The idea is that there's no path. So what do we do between U and V? Here's our picture. Looks a bit like this, right? If U belongs here and V belongs here, then there is no path between the two of them. So the idea that I have in mind is that, okay, we'll define again H prime, right, to be everything outside of HU. Right, so everything else. Now this H prime may or may not be connected. We don't know. But one thing is for sure. Since HU is connected, it has to be connected. And it is acyclic because it's a subgraph of an acyclic graph. Right? We used the result there just now. HU is a tree, which means that the edges equals to the vertices minus 1. It must equal the vertices minus 1 because it's a tree. Now, for HV, we don't know whether it's connected or not. But here's the beautiful thing. If HV is connected, well, not HV, H prime. If it is connected, right, we know that H prime cannot include U, right? So more precisely, U is not in V of H prime, which tells us that V of H prime has to be less than or equals to K. Right? It has to have at most K vertices because it cannot include U. So in other words, we can impose this. And we know that either H prime is connected or not connected. Now, if it is connected, that makes H prime a 3 because H prime is acyclic as well. And we get equality. Right? But if it is not connected, then it is, well, if it's not connected, that means it's smaller. It's basically this statement but smaller, right? It's actually this statement, it is not connected and it's not cyclic, but smaller, right? So therefore, by induction, we get the inequality. By the induction, we get the inequality. So that's pretty cool as well. So we can now, again, very similar to one of the previous results, regardless of what you believe in, you do know that E of H prime is bounded above by V of H prime minus 1. You definitely will know that result. Now what that tells us, right? What that tells us, I think, by the way, we could have used this for one of the previous questions actually. That would have been a lot more convenient. Yeah, I think we can prove it this way. So now as we get rid of the cycle, essentially we throw away the cycle, and I think I'll go back to that proof. Yeah, I'll go back to that proof because there's a much better proof for that result, for the bigger than version. Yeah, okay. So we'll go back to that proof, but for now, this tells us that we can conclude that the total number of edges in the graph is, well, it's equal to the edges in HU plus the edges in H prime. And what this means is that it is strictly upper bounded by VH U plus VH prime minus 2. You can check this upper bound using these results. And this means, well, this will give us V of G, and minus 2 will be strictly less than minus 1. And that's how we prove this result. In fact, I want to use this result and go back to the previous result because we can now use the exact same trick to prove that previous result, which I was struggling for so long for, trying to define everything properly. Let's go back to the previous result right now. So let's come back to this one. And I'm gonna now prove this in a much more quicker manner. Sorry, not this one. Let's go back to this result. This one. Alright, let's come back to this result. And yes, we're still going to prove by strong induction. And here's the idea. We're going to let C denote the cycle that we know that G is cyclic, right, in this context here. So once again, we are trying to prove this result. And now we know how to do this a bit more clearly. So suppose since G is connected and cyclic, it contains a cycle C. Okay, it contains a cycle C. Oh, actually, we can use the we can use the other way. Okay, it's all good. Okay. Okay, so now we can define it. We can do it. Okay, so define H prime to be the graph that basically throws away the cycle. We're going to throw away the entire cycle. And clearly, this might create a few problems, right? This might create some problems for the induction, because how do we know that what remains is connected or cyclic or whatnot? Well, one thing we do know is that it has connected components. We do know it has connected components. Okay, this is where we're gonna use this trick, right? So let's suppose a few cases here. Right, we have a few cases. First case, H prime is connected. Right? Second case, H prime is not connected. Okay? Now, if H prime is connected, we still have two cases, right? We don't know whether it is cyclic or acyclic. Right? We don't know whether it's cyclic or acyclic. Now, if it is cyclic, then we can use induction. And here we're working with the fact that, here we are making the assumption that V of G excluding V of C is non-empty. Then H prime has at most k vertices, and we can use induction to conclude that E of H prime is strictly bigger than V of H prime minus 1. Right, for a cycle, we do know that E of C will be bigger than V of C minus 1. So that's definitely going to be in the mix over there, right? Then we can in fact, we're gonna go a bit more stricter over here. We do know that E of C is equal to the number of edges in a cycle equals the number of vertices in the cycle. Okay, so we can do that. Now that is if H prime is cyclic. If it is acyclic, then we know that H prime is a tree, which means that you have E of H prime, right? E of H prime equals to V of H prime minus 1. This should help you finish up the argument. Right? But now what happens if H prime is not connected? So I'm thinking a little bit like this. Here's a cycle. H prime looks a bit like this. As in, this is everything. If we were to get rid of the cycle, we basically get a bunch of disconnected graphs, right? So, well, we get H prime being disconnected. Well, then here is going to be my A. Okay, I think I have an idea. Now, if H prime is not connected, and now of course suppose it has its own cycles like this. Right, suppose it has its cycles over here as well. I think technically we also need to get rid of any edges that connect to H prime. Yeah, so basically actually this argument doesn't really work. I mean, you have to basically also get rid of these guys. Essentially, you have to get rid of these guys, which is a bit, takes a bit of effort to sort of establish the argument. So, it doesn't work here. So, I guess the takeaway here is that sometimes, if you can find a more efficient proof, go ahead. If you can't, hey, you have to try on some things. The high school mentality is always, give me the formula to answer the question in 10 seconds. And I'm like, I'm sorry, that's not how math works, at least not at this level. Perhaps some of the past year papers might be able to help, but in general, math proving can be a highly non-linear process. So it doesn't work. I think there's a way to make it work, but it takes a lot of effort, and we have to finish the rest of this tutorial first. So there's that. But we do have this result over at the bottom. We do have this result over here. So we do get this result by chopping it up using induction. The previous result takes a lot more effort to chop up using induction, but it's doable. Okay. Now, so previously, we have actually very painfully proven that if G is connected and cyclic, then the number of edges will be strictly bigger than the number of vertices minus 1. Here, if we were to take the contrapositive, we're going to get the number of edges being upper bounded by V of G minus 1 implies that connected and cyclic. I think we got the wrong result. Give me a moment. It's not connected. Okay, that means G is not connected or acyclic. I think I made a mistake in what I wrote over here. I think there's a subtle error here. I think the question here is supposed to be G being not connected. I think is G being not connected. I think this is the claim, if I'm right. I think I copied the question wrongly, but I believe that is the correct claim. Okay, so here's the claim. Oh, sorry. Oh gosh, I'm not doing well today. This is the claim. And for this one, the claim goes this way. So, pardon me, let's try that again. So, we've proven before that if G is not connected, if G is not connected and acyclic, then we are going to get E of G being strictly less than the vertices minus 1. This is going to be the case. So if we were to take the contrapositive, we're going to get E of G bigger than equals to V of G minus 1 implies that G is connected or G is cyclic. And here the claim is that you only get connectedness. You instantly get connectedness. And here's a trick. This implication, if you know G is connected, you know that it's connected or acyclic. But if it's connected or acyclic, you don't know which one. You don't know whether G is connected or G is acyclic. You don't actually know which one. You know it's one of the two. You don't know which one it is. And what that tells us is that most likely this is going to be false. And the counterexample, is going to look like this. There we go. So you can check that there is one edge, there are two vertices, so this inequality works because 1 is bigger than 2 minus 1. This is correct. And yet, G is clearly not connected. So that's our counterexample. And likewise with the next result as well. So this result as well, okay, that's why getting the statement correct is really important. We've proven before that if G is connected and cyclic, then the number of edges will be strictly bigger than the number of vertices minus 1. So taking it contrapositive, we'll get that if the number of edges are upper bounded, then G is either not connected or not cyclic? And once again, the answer is false. And once again, we have the exact same counterexample. Here we have 1 being less than or equals to 2 minus 1. And yet, it's actually still cyclic. Well, it's still cyclic because it still has a cycle here. Now, the idea here is that basically, you notice the difference, the discrepancy in the conclusion. That actually tells you where the counterexample is probably going to lie in. That probably tells you where you're going to find some problems. Okay, so that was faster than expected, although the first parts were a little bit long. It took a little bit of effort. Alright, now this question is a really useful application of trees inside computer science. This is called the minimum spanning tree. It's a really useful idea. So we want to draw all the spanning trees of this particular graph. And what is a spanning tree? A spanning tree is a subgraph that is a tree that actually hits every single vertex. So for example, the spanning tree in this instance is going to be 1, 2, 3, 4, 5. We have a few actually. 1, 2, 3, 4, and 5. So now for any spanning tree of this graph, it has to get from 1 to 2. But that's the only path, right? Those are the only paths. Likewise, with 1 to 5. 1 to 5. Now, to hit 3 and 4, there are actually a bunch of ways to do it. And this actually would let us ask a very interesting question called the minimum spanning tree, right? So one way to do it is to go to 3 to 4. Another way is to go from 4 to 3. They are isomorphic, fair enough. Last one is go directly 3 to 4. And you might want to ask which one is the minimum spanning tree in the sense of, okay, if these items each have some value to it, how can you minimize the total cost? Right, so that's a very useful idea of a minimum spanning tree. I remember learning this in the course that I took on data structures and algorithms. Now that's a spanning tree, roughly speaking. So in other words, you have a tree that spans the graph. I mean, that's what it's in its name. It's a spanning tree. It's a tree that spans the graph. So let G be a finite tree. We claim that G has exactly one spanning tree. One and only one. So here's the proof. So let G be a tree. Then isn't it interesting that if G is a tree, then G is the only, well, it's not the only, but G is a tree and it spans G, right? So therefore, G is a spanning tree for G. Right, G is spanning tree for G. Now, of course, we're claiming that this is the only one. So, suppose for contradiction, that there exists some tree T, which is not the same as G, such that T spans G. Okay, so suppose for a contradiction that there exists a T not equals to G such that T must span G. We do know that T is a subgraph of G. We know T is a subgraph of G. Right? We do know that it is a subgraph of G. Okay, I don't even think we need to worry too much. Let's do it this way. Let's argue slightly differently. Let T be a spanning tree for G. Our claim is that T must equal to G. That's the idea. And some of you might see where I'm going with this. I think some of you might see where I'm going with this. Well, if G, okay, so since T is a tree, it is connected and Well, since T is a tree, it is connected, right? Right? So T is connected. See, if T is a tree, it is connected. Well, since G is a tree, it is connected as well. Right? Since G is a tree, it is connected. And the idea here is that if G is connected, it can only have one connected component. Right? It only has one connected component. Okay, wait. We might need to regroup here a little bit. Because connected components doesn't really tell us about acyclic. Doesn't tell us anything about it being acyclic. Right? Okay. Part of me. Okay. Let me think. Okay. So let's just try something. Okay. So then T is a subgraph of G. T has to be a subgraph of G, and the idea I have here is that it's sort of a connected component, but I don't think we can really work that out. I'm just gonna use but G is a tree. Alright. So now T is a subgraph of G, and I think I have something here. Right? I think I have something here. Okay, so here's the idea. Okay, so T is a subgraph of G. That's all well and good. G is a subgraph of itself as well, right? So G is a connected subgraph of G, right? G is a subgraph, connected subgraph of G. So if we can show that that T is a connected component of G, if we can show this, we're good to go. Okay, so that's the idea there. If we can show that it's a connected component, then we're good to go. Okay, so here's how we're gonna do it. Right, so how do we show that T is a connected component? Okay, since so we'll let V be in VG, and since so then, okay, there we go. Then there exists a connected component, HV, that contains V, and this connected component is a subgraph of G. Right? Okay. Which means that it is acyclic, which means that HV is a tree. Okay? So the idea is that X, that V, okay, so in other words, the connected component containing V is a tree, right? Now, of course, we claim that this is basically everything. Now, okay, I think we have an idea here. Okay, since T, right? Since T contains X, right? So T contains X and X lies inside HV by the eating up lemma, we get nothing. Okay, never mind. Let's just try something a little bit more rudimentary. Never mind. Probably should go take a break soon, but it's okay. Let's just finish this and we'll be good to go. Okay, so let's try that again. So T is a subgraph of G. Suppose Okay, so let's do this way. Suppose t is not equals to g, right? Then t is not equals to g. Then there exists an edge that belongs into t, but it does not belong to g because it has the same vertices. So then you must have either one. Okay, in fact, it should be the other way around. Sorry. Suppose t is not equals to g, then since t is a subgraph of g, we do know that the vertices, in fact, the vertices by definition of a spanning tree must be the same, but the edges will be a subset. So since we know that there's a subset, then there exists some edge, say xy, inside E of g, such that xy does not belong inside E of t. Right? That's gonna happen. And okay, I know what we're gonna do now. So this tells us that since t is a tree, which means it's connected, right? There exists a path from x to w to y, right? Inside in t, right? We can go from x to y in t, which means in g as well. This tells us that x to w to y, x is a cycle in g, which means that g is cyclic, a contradiction. So once again, here's the idea. If x and y are not directly connected because t is a tree, it has to connect them eventually. But if you rejoin them up, you're going to get a cycle, which is a contradiction. Right? That's a short, relatively straightforward proof, no eating up lemmas or whatever. Right? But that works. So in other words, for any we've shown that t cannot equals to g. And we get a contradiction, right? So therefore, the conclusion is that t must be equal to g. Any spanning tree for g is precisely just g. It's the only one. Otherwise, you get a contradiction. Now we can go the other direction. So suppose g has exactly one spanning tree. One spanning tree. Then g must be a tree. Then g is a tree. Right? So here's my proof. Right? So if g has exactly one spanning tree, we'll let t be the spanning tree for g. And this tells us that g must be a tree. Now, if t is a spanning tree for g, this tells us that t is a connected subgraph of g. And you can use t to check that, and I'm going to give this to you, that g is connected. All that remains is to check that g is acyclic. Right, so all that remains is to show that g is acyclic, and here's a proof of that claim. Okay, so how do we show that g is acyclic? Well, we're gonna suppose g is cyclic and contains a cycle x to w to y x. Okay, so it looks a bit like this. Looks a bit like this. Roughly speaking, we're going to use this to show that we can in fact get more than one spanning tree. Alright, that's the idea. We're going to try to use this to show that we get more than one spanning tree. And how do we go about this? Suppose G is cyclic. Can we use one of these other results for... If G is cyclic, can we use... Do we have a result on the bounds on... Yeah, we do, but we don't really... It's not very useful for our purposes because we can't really bound things that cleanly. Okay, no fear, have no fear. So suppose G is cyclic and it contains a cycle. We know that T has to connect everything together, correct? So, I'm thinking of how to argue this situation. It's not as straightforward a situation as I hoped it to be. If G is acyclic, suppose G is acyclic, right? Or rather, we're trying to show that G is acyclic. I mean, the idea is this: T sort of attaches itself to everyone, right? And this is the only one. So if it is cyclic, then you have more than one tree created by this cycle. Correct. Okay, I think I have an idea here. I think I have an idea here. Okay, so since T is a spanning tree, it'll be connected, which means that there exists a path P from X to W. Right, there will be a path from X to W. We'll call this P1. And there would be a path from P2 from W to Y. Right, so there's going to be these paths over here. Okay? Yes, we're going to get paths from X to W and then W to Y. Right? So, and we're gonna assume that all of these guys don't intersect, right? We're gonna assume that they don't intersect. Okay. In fact, I might label it this way. It's not just W. Give me a moment. Let me think. Or maybe we should do it this way. X. Okay, so all the way to say. W minus 1. Okay, I'm going to call this guy W minus 1. And I'm going to call this W1. And there exists a path P2 from W to Y. Right, so that's the sort of the idea over here. Okay, I think we are good to go. So this is a tree that sort of makes this connection. Okay, we can define T prime to be we'll define T prime to be this particular graph, right? It's going to be the same graph as before and the same edges, but now I'm going to basically chop off W1 and I'm gonna include XY. Okay. Yeah. So that's my idea. Okay. So I'm gonna chop off W1. So we're gonna include XY, but we're gonna chop off W1 like this. Right? So you can check that it will still be connected, right? So let me just very quickly ascertain this fact. Yeah, this looks pretty fine, right? So you can check this out. T prime is connected, and in fact, T prime is connected, right? And furthermore, it's acyclic. I think to show that T prime is connected is not too hard. To show that it's acyclic, oh my gosh, E of T is E of T. There we go. There we go. Then that way, you will get T prime will be connected and acyclic. So I'm gonna let you guys check that out yourself. This one shouldn't be too bad. It shouldn't be too difficult to check. Which tells us that T prime is a distinct spanning tree from G. But that means G has at least 2 spanning trees, which is a contradiction. It has to be a contradiction, right? So that is the sort of the idea that I have in the back of my mind. The idea is that you chop off one edge and you compensate it with another edge. Everything will still be connected. All of these guys will still be connected. If you chop this and you include this, they're still going to be connected. It's still going to be fine. It's all going to be good, right? But there's a subtle error in my ways over here. This part over here is a little bit dodgy, because how do you know the spanning tree actually passes through the cycle? It might not have actually passed through the cycle. So I'm gonna have to retry this argument here. Let's try it again. I think we can do it. It's not too bad. Okay. Of course, we require a bit of effort, and that's part of the math process, but it is what it is. So the claim is that G is acyclic. And how do we go about it? Maybe a picture would help, right? So here's a picture. Right. Here's the picture. Right. If it only has one spanning tree, right? If it has only one spanning tree. So I'm thinking, can we try to make the case that G is acyclic? I want to use a connected component argument here. But I have no idea how to make the case here. Right. Yeah. Now G is connected and it contains T as a connected subgraph. But how do we know that T is a connected component? If T is a connected subgraph of G, right? And can we have T containing G? Can we have T containing G? That is the question. Because we want to claim that T is equals to G, right? That's our claim. Our claim that T must be equal to G. Now G is acyclic. Let's just see. Suppose otherwise it has a cycle that looks a bit like this. This is really irritating. I mean, alternatively, we could try to show some form of a contrapositive. So like if it has more than one spanning tree, then it must be cyclic, right? So that might work. I think that might work. If it has more, no, the other way. Sorry, that's the wrong argument. If G is not a tree, right? Then it has either no spanning tree or more than one spanning tree. So that's the idea there. No, it's fine. Okay, let's just start with G being acyclic. Let's just claim that G is acyclic, and let's oh, I think I have an idea. I think I have an idea. Okay, I think I have an idea. Okay, so let's go with the same idea as just now. So let C be a cycle that G contains, right? So my idea is this: the tree either will span all of these items like this, right? Or it will span from the outside. It will come in from the outside, right? So that's the idea there. Or should we prove by induction? That'll be hilarious if we can prove by induction. Although part of me thinks it's possible to prove by induction. Nah, let's not use an induction argument here. Okay. Let C be a cycle that G contains that looks a bit like this, right? For example, either the cycle lies like this, right, or it involves some of the edges of the tree. In fact, if it's a cycle, right, let C be a cycle, because we could get a cycle that looks a bit like this. Something like this, right? And then in this case, T just has no business with these edges. Okay, let's try this. Then there exist 2 points in the cycle, X and Y, in the cycle with 2 paths, P1 and P2 in G. Right, so here's the idea. X and Y, you should be able to have 2 paths. Correct? So the idea is to sort of try to define a new spanning tree that doesn't really involve this. Unless we can show that G is a subset of T. If G has exactly one spanning tree, oh, how about this? Let C be a cycle, then we can write C as X all the way to W all the way to Y, right? So that's the idea, right? And then, well, YX to be more precise. So we have one path this way and you have one path this way. So the original graph, right? Let's observe this. Either we can go to X and Y from different paths. Okay, so something like this, right? Either here's X and here's Y. Either we'll go to it by different paths, like this, or we're going to incorporate the path into Y, from Y into X, right? So that's sort of the idea. We have 2 cases over here. So we have 2 cases. T contains X, Y, right? T contains X, Y, right? then let's just say you have some other guy over here, some other guy here. Right, so the idea is that you can try to, instead of going from y to x, you could go through some other means. Right, you could get rid of this point, and then you could attach it to something else. Okay, I think we have an idea. I think I have an idea here. Okay, so let's do something like this. Okay, this should be pretty clean, right? So we have a wxy that looks like this. Oops, gosh, that was awkward and embarrassing. Okay, wxy, right? Either we're going to go directly this way, right? In which case we can just chop this off and come down here, right? Because we know that t is a 3, and we can create a new guy, right? Or we do know that we're going to connect to something else that connects to y, right? In which situation we'll chop off the connection to y and connect to x. Okay, I think we've got a good idea here. Okay, so suppose t contains xy, right? Either t will contain xy or not, right? So if t contains xy, then define t prime to be the same vertices and the same edges, but now we include wy and chop off xy. So we're gonna include this guy and chop off this guy, right? So that's the idea here. We're gonna include this guy and then chop off this guy, or more precisely, we'll need to draw a connection this way, right? So okay, maybe we can be a bit more precise here. So since t contains xy, this tells us that xy belongs into the edge set of t, which tells us that wx cannot belong. Okay, so what do we have here? So we'll let w, okay, well, we've used w, so let z be a vertex such that zy is connected. We may or may not have a connection there. Okay. This is problematic. This feels like this is what happens when I struggle when I write an English essay. Like I have so many ideas and yet they're all problematic, and it's like not helping me out here. Okay, let's see if we can try to make any other claims. Okay. So what do we know about acyclic? Acyclic means there's no cycle, correct? So in other words, between any 2 points, you can only have one distinct path between them, correct? So let's try that out. So fix x and y inside v of g. Since t is a spanning tree for g, right? There exists exactly one path from x, between x and y, right? If you have more than one path, then the thing will be cyclic and it's not gonna work, right? You have exactly one path between x and y, right? This is true for any xy. So fix xy. Now, okay. I think we got it. Okay, so suppose G is cyclic, then let x, w, y, x denote the cycle, right? And then, since x and y belongs in the tree, there exists a unique path, right, from x between x and y in T. Correct? Between x and y in T. Okay, maybe I shouldn't use this argument. I should use the previous argument. I don't know what's wrong with this. The previous argument seemed to work out better. Okay, so sorry. Let's try it again. So fix x and y in the vertex set of G. Since T is a spanning tree for G, there is a unique path between x and y. So, since there is a unique path between x and y, if there exists a different path from x between, more precisely in T, if there exists a different path between x and y, then we can obtain a different spanning tree because we're going to get different edges. Right, we're going to get different edges. Let me see if I can try to make this a bit more clear. This is a cycle. Oh, wait a minute. I noticed something interesting. Oh no, we got nothing. Suppose there exists a cycle x to w to y x. I want to say, roughly speaking, that you're going to get this particular situation, right? So the idea is that you can go to wyx, and then your tree is gonna have to pass through w in order to get to y and x. Either it has to pass through w, or it does not, or it passes through some other route, right? So I don't really know how to make the argument airtight as much as I wished. Claim it is acyclic. I'm thinking, what other results can we use from it being acyclic? Because if it's connected and cyclic, we could try to bound some of the results. Right, we could try to bound some of the results. I think we can try something. We can try some bounding arguments. So this tells us that the edges of T has to be less than the edges of G. Right, okay. So I'm going to try a bounding argument. So suppose G is cyclic, then the number of edges then G has to be connected and cyclic, which tells us that the number of edges is bigger than the number of vertices, minus 1, right? Which is equal to the number of vertices of T, minus 1, right? This is true, which is equal to the number of edges of T. And okay, so we definitely know that it has at least one more edge. Okay, I think this might work. Okay, I think this might work. Okay, so here's, this is fun. Finally, we're making progress finally. So since G is cyclic, the number of edges in G has to be strictly bigger than the number of edges in ET. So therefore, there exists some edge xy inside EG such that xy does not lie inside ET. Right? It does not lie inside ET. Okay, now this is where I think we can make some progress. So here's the idea. For the 3T, it looks a bit like this, right? Ooh, yes, I think we are good to go. Okay, so what we'll do is, okay, so I think we can make this argument. So we'll let W be a vertex, such that Wy is inside E of T. Okay, so maybe we can make this a bit more precise. Okay, so here's how we're gonna do it. Oh, finally, since T is connected, there exists a path X all the way to Wy. Right, let's just put Wy, again highlighting this situation here. Now we can define T prime to be the spanning tree with the edges of T, all the same edges, except now we're going to connect it this way instead, right? So we're going to essentially, we're gonna cut off the connection. Pardon me. We're gonna cut off from W to Y and connect to XY. So we're gonna include XY and cut off W and Y. Right? So I'm going to leave you to check that this guy is still a tree. This is still a tree. So claim T prime is still a tree. Right? And furthermore, V of T prime equals to V of T, which equals to V of G. Right? So the idea is that if this guy is still a tree, and you can make the case because it will be connected and it will be acyclic. It will be acyclic because, yes, you can't form a cycle. Yes, this looks good. Okay, sounds good. Woo! Alright. So T is still a tree. I'm gonna let you check this claim for yourself. Okay, you are gonna check this claim for yourself. Vt prime equals to Vt equals to Vg. So therefore, T prime is a spanning tree for G, and T prime is not equals to T because the edge sets are completely different. Therefore, G has at least two spanning trees, which is a contradiction. And that's that. Okay, that took a lot more effort than I hoped it to be. And we are like at 3 hours already, and it's getting quite tiring and long, and I can see why this might not be the easiest one to follow along, but it's fine. Okay, now finally we want to talk about this idea of a rooted tree. So here's the number of rooted trees. We're going to count the number of rooted trees with n vertices if we count isomorphic rooted trees as 1. Isomorphic meaning same shape. So we've already seen before that in the case for n equals 1, we have such a tree. We have these trees which are isomorphic to one another. Right? For 4, we have this and this. Right? So for 4 vertices, we have 2 different shapes. Rooted trees tell us that we can select a particular vertex as a root. So in this case, for n equals 1, we have 1 rooted tree. And we usually will use an open circle to denote the root. For n equals 2, we could choose either vertices as the root. And we're going to get either this or this. But in either case, they're isomorphic because you can imagine them swinging downwards to form you this rooted tree, right? So both of them, if you swing this down this way, swing this down this way, it's going to be isomorphic. So we only still get just 1 rooted tree over here. For n equals to 3, we can choose any one of these guys, and the results will be slightly different. If we chose any of these ends, we're going to get these rooted trees. But if we chose the middle guy, then we're going to get this rooted tree. So as trees, they're all still isomorphic, but as rooted trees, they are not isomorphic because this guy has 1 child and this guy has 2 children, right? So that's the rough idea over there. And likewise for n equals to 4, there are more rooted trees to consider. I'm just going to draw them over here really quickly. This is if we were to make these 2 the roots. If we made this the root, then we're going to get this situation. There we go. If we made this the root, or this, we're going to get this situation. Same shape, basically. And finally, we could make the center guy the root, and this gives us this shape. So we do have 4 different rooted trees here. So it's 1, 1, 2, and 4. These are the number of rooted trees that we have. Right, so the idea is that we have a root, and from the root, we get everyone else. Again, useful in the CS areas. Okay, we have a bunch of definitions here. I'm not gonna really spend too much time on the definitions because these are notations essentially. These are essentially notational bits. Well, not very convenient. So perhaps you could just ask for... Oh gosh! You know, this is really annoying. Oh boy. Okay, let's try that again. I pity the kids who are crying, and I pity myself for being here. Woo! Alright, let T be a finite rooted tree of height h, in which every vertex has at most 2 children. Then T has at most 2 to the h terminal vertices. So what does that look like? Start with the root, and suppose I have 2 children. And suppose these guys have 2 children, or 1 child, or no child. Doesn't really matter, right? So something like this, maybe you have 1 child, maybe you have 2 children, whatever. The claim is that the number of vertices, right, is at most 2 to the h. Alright, so here's our proof. We're gonna do induction on the height. We're gonna do induction on the height. So in this case, by the way, I drew 1, 2, 3, 4. This will be h equals to 4. I drew a graph for h equals to 4. Induction on the height h. So the base case is for h equals to 1. Then we have a total of, well, 1 vertex, right? Then we have v of t is basically the root. I'm just gonna use root here, which means that, well, since, well, more precisely, we can do it this way. We'll let r denote the root of the tree, and we're gonna, by the way, call this h equals 0. We start from the 0th level. Since h equals to 0, r has no children. I think we can make this more vigorous, but I think this is pretty intuitive, and the idea is that, yeah, there's no child, right? There is no children over here, and so you could prove by contradiction. If it has children, then you can prove by contradiction. If it has children, then the longest path from the root to any child will be bigger than 1, so the height has to be bigger than or equals to 1, which is a contradiction. So r has no children, which means that the tree has only the vertex r, which means that v of t equals to 1, which is less than or equal to 2 to the 0. Right? So that's for the h equals to 0 case. Now what about the h equals to k plus 1 situation? Right? So the idea here is to sort of take the root over here and cut them out. And once you cut them out, this guy will have height less than or equals to k. This guy is also going to have height less than or equals to k. Both of these guys are going to have heights less than or equals to k. And so once we have that, we can apply induction. Okay, so there are ways to make this argument a lot more technically correct, but I'm just going to go with this argument because I think it works out very well. So in the h equals k plus 1 case, once again, we'll let r denote the root of the tree. And since h is bigger than or equals to 1, r has at least 1 child. Right? R has at least 1 child, u. Okay, it has at least 1 child, u. It may have another child, v. Okay, and in fact, I'm gonna prove, suppose R has 2 children, u and v. Okay, I'm gonna leave the case when R has exactly 1 child. I'm gonna leave you to check this out on your own. Okay? I'll leave that to you to figure it out. So now suppose R has 2 children, u and v, then we'll define new rooted trees. Right? So then what we'll do is we'll define h prime to be the original graph, or rather we call this h. We'll take the original graph and get rid of the root. We'll get rid of the root, and then for the edges wise, we'll get rid of r u and rv. Okay, so that is going to be the situation. That's going to be the sitch. You can check that. Okay, so here's some homework for you. Okay, this part's homework. Claim H will be equal, or rather, V of H is going to be V of HU union V of HV, and E of H is equal to E of HU union E of HV, and furthermore, these guys will not intersect. I think we've proven this a few times before. We've connected tree graphs and whatnot, but you can check this yourself. So here's a claim. Now we can let U be the root of HU and V be the root of HV. And now, I'm gonna let you check this as well, that the height of HU is less than or equals to K, because essentially the longest path now from R to everything else, instead of the longest path is from R to U to everything else, used to be K plus 1, so this guy should be less than or equals to K. So you can go and check out the argument yourself. I'm going to just leave it as exercise over here. Okay, I'm going to leave these as exercises. Claim that the height of HU is less than or equals to K and the height of HV is less than or equals to K. So therefore, by induction, right, the number of vertices in HU has to be upper bounded by 2 to the K, and the number of vertices in HV is upper bounded by 2 to the K as well. So that is essentially the key argument of the proof. And now finally we need to wrap it up properly. Alright, so finally, since G is a tree, right? Since G is a tree, V of, well, the number of edges, the number of edges is equal to the number of vertices minus 1. Okay, let's just see if I can do this more conveniently. Then V of G will be equal to V of HU plus V of HV plus 1. Alright, it will be plus 1. So this will be this could be a problem. Wait, what's the question? Terminal vertices. Terminal vertices. Gosh, that's very embarrassing. Oh gosh. Then the terminal vertices of G are the terminal vertices of HU union the terminal vertices of HV, and this tells us that the terminal vertices of G will be upper bounded by, oh gosh, this is not correct. This is the terminal vertices of HU. And this is the terminal vertices of HV. It's not HU and HV. It's not that. So the terminal vertices of G is the sum of these guys. And that's that. Now, the technical proof, there are lots of gaps to fill up, but I'm going to let you guys fill in the details on your own, right? So to show how you continue the proof, if R is exactly one child, it's almost the same argument. In fact, yeah, there's a way to argue it. And then same thing with the claims and all that good stuff. So you can check this out on your own. This seems pretty straightforward. This as well, right? But you need to check using the definitions of the longest path and all that good stuff. So The height meaning what's the longest path, right? The length of the longest path from R to any other, from the root to any other vertex. Okay, that is very long and it's very tiring, and I have a few more results to go. No. At this point in time, it's just a slugfest. I get it, but sometimes it's like that. So we let T be a finite rooted tree of height h in which every internal vertex has exactly 2 children. Suppose T has exactly T terminal vertices, then T has exactly T minus 1 internal vertices, and we will have this in total. So I think this is the main part. T has exactly T minus 1 internal vertices. Let's draw a picture. So looks a bit like this. Each vertex must have 2 children. Each internal vertex must have 2 children. And the idea is sort of like when you extend out, you sort of create. Here's the idea, right? So suppose now we have this number of terminal vertices. We have 1, 2, 3, 4, 5, and 6. Suppose you have 6 terminal vertices at this moment. The idea is that if you were to sort of chop off 2 of the vertices, right? So you chop off 2 of the vertices, or rather you chop off 2 of the vertices, you chop them off, then you should be able to apply induction on the remaining. Now that's one approach. The other approach is once again to chop off the root. I think chopping off the root is cleaner because we don't have to worry so much. So once again, we'll prove by induction. This time we're gonna do induction on T, I think. Yeah, we're gonna do induction on T this time around. Okay. Yes, we're gonna do induction on T. So now firstly, base case, T equals to 2. And I'm gonna let you check why we cannot start with T equals to 1. Alright, so T equals to 2. So in other words, the tree has 2 terminal vertices. Actually, should we do induction on T? So I'm thinking might be better to do induction on the height of the tree instead. Yeah, I think we'll do induction on the height of the tree. That makes more sense, right? When it comes to rooted trees, it's best to do induction on the height of the tree. So base case is when ht equals to 0. In fact, we cannot go ht equals 0. Oh no, ht equals 0. Then the root R is a terminal vertex. Therefore, of T, therefore this implies that T has 0 internal vertices, but this simply means that it is 1 minus 1. In fact, R is the terminal vertex of T. This is the only one because the height is 0 once again. Right, so you can check that as well. So T has 0 internal vertices, which actually proves the result. Now for the base case, well, we've done the base case, so what about induction hypothesis? Suppose true for all trees with height less than equals to k. Now we will suppose that h of t is k plus 1. Again, here's the key idea. We're going to take the root and we're going to chop it up. Right? So since ht is bigger than or equals to 1, R has 2 children, u and v. We're going to once again chop them up just like before. Right? So we'll define h to be v of t excluding r, and the edges excluding ru, rv, because we're going to call this u and v. Then once again, we can informally say that hu and hv constitutes h and is a disjoint, and more precisely refer to the previous question where we define this sort of a bit more formally. And the height of hu, right, these are all trees. hu and hv are trees, and their heights has to be, if the whole thing, the height is not more than k plus 1, then this heights must be not more than k, right? Not more than k. So by induction, the number of internal vertices in hu is equal to the number of terminal vertices in hu minus 1. Well, that's what we mean, right? The number of terminal minus 1 should give us the internal. That's the induction hypothesis. And we can repeat the same thing for hv. And at this point in time, you might be wondering, wait a minute, how do we sort of continue from here? Well, if we look carefully, in the new graph, u and v are not considered internal, they're not considered, more precisely, u and v are internal vertices. The terminal vertices are the same, but in the original graph, r is an internal vertex as well. R is also an internal vertex. So therefore, the number of internal vertices in G is everything here and everything here, including R. So that means it's the number of internal vertices in HU plus the number of internal vertices in HV plus R. Alright, that is the total number of internal vertices over there. So we can substitute these numbers . Stuff cancels out, and we are left with number of terminal vertices in HU plus the number of terminal vertices in HV minus 1. But here's the beautiful part of this setup. What are the terminal vertices of U and V? It's actually the exact same terminal vertices of G. So this whole thing actually gives us the number of terminal vertices in G subtracted by 1. And we're good to go. I just realized we have one more question. I'm not done. This reminds me of the time I did like 6 hours of epsilon delta. So like, what was it? 6 hours of linear algebra. Oh my goodness, that was mad speed runs there. Last question for the day. Let T be a finite tree with at least 2 vertices, then T has at least 2 vertices that are in exactly one edge. Okay, here's a very quick proof, and my camera is gonna run out of battery soon. It's interesting that they gave the announcement there. Let T be a finite tree with at least 2 vertices, then T has at least 2 vertices that are each in one edge. It looks a bit like this, by the way. So you have something like this. See, like that, look at that. And you can definitely find, say, this path, or this path, or this path. Now what's interesting about this proof is that we can now try to use some of our machinery to help us. So we'll let P be okay, so we'll define this way. Any path inside this guy must have length at most the number of edges, right? I mean, at most, you can only have at most the number of edges. So every path in T has length and is a tree, right? So it's at most the number of edges. Right, or in this case, it will be the number of vertices minus 1. You could get a situation where the longest path looks like this. Alright? So we're going to define the collection of integers L such that there is no path of length L. And you might be wondering, why do we define it this way? Because we know that every path has this length smaller than or equals to this guy, right? It has to be bounded above this way. This tells us that there is no path of length Vt, which means that Vt lies inside L. And why do we purposely show that Vt lies inside L? It's because we can say that L is non-empty, and therefore L has a minimum element, say M. What does this mean? If L has a minimum element M, then there is a path of length at most, in fact, of length M minus 1. And this is going to be the maximum length. Right? So why is that the case? Because if L has a minimum element M, then M satisfies this criterion. In other words, there is no path of length M, but M is the minimum number. So for any number smaller than M, there is a path of length M minus 1, for example. And if you think about it, that has to be the largest, right? And I'm going to let you check that this will be the largest. The idea is that anything you have lengths that can be of M minus 1, M minus 2, M minus 3, so on and so forth, but M minus 1 is the biggest. So it has length of M minus 1, maximum length. So we'll denote this path by x0, x1, all the way to x m minus 2, x m minus 1. We'll call this u, and we'll call this v. Claim. U and v belong to exactly one edge. Right? In fact, we could make the case that u belongs to one edge only, to ux1 only, and we could similarly prove that v belongs to xm minus 1 v only. I'll let you check that. So that is the claim, and here is the proof. If u belongs to some other edge, say w, we have two cases. So suppose u belongs to some other edge w where w is not equal to x. We have two cases to consider. Either w belongs inside one of the items in the path, right? Either that happens or that does not happen. Now, if it happens, then we're going to get u x1 all the way to xm minus 1, or rather, all the way to w, u being a cycle inside the tree T, which means that the tree is cyclic, which is a contradiction. And if W does not belong inside this set, then the path, right, the path W, x1, x2, all the way to, WU, x1, x2, all the way to xm minus 1, y, has length m, which is a contradiction as well, because we've shown that there is no path, right? There is no path with length m. Contradiction as well. So therefore, this claim must be true. And we are done. And that is it. That is all of the questions that we have for trees. It's a bit more tedious than the previous one, but the key element that I like to sort of convey is the aspect of induction, where if you cannot solve it in general, just go and prove it using induction. You can get away with most proofs via induction. That is it for discrete math. Thank you all for watching this stream. If you enjoyed it, and if you struggled through it, let me know how you felt in the comment section below. Remember to like, comment, subscribe. I can't believe I'm doing this in a stream. And I'll see you guys when I see you guys.